Thank you for joining us. To announce our next speaker, Allyson Scott is an applications engineer for Celera Motion. For working with precision motion components, she was an applications engineer at Thermo Fisher Scientific. Allyson is now focused on providing motion control solutions for customers and creating technical documentation for Celera Motion's motors and mechatronics group. Welcome, Allyson.
Thanks, Nick. Yeah, that's a bit of a tongue twister there. Well, hi, everyone. Thanks so much for joining me today. I'm really excited to be able to speak to you all, and especially to be able to speak to you all about this topic, which is so cool. And I hope that you guys enjoy it as much as I do. So with that, let's jump in. During this presentation, I'm going to be introducing the technology behind Talbot imaging and why it's utilized in high precision optical encoders. So in a closed loop system, you have a motor, which is driving a load, and you have a feedback device, which is used to measure the actual position of the load. Now that actual position is compared to a commanded position, and the position error is then used to drive the load to a new position. So there are many options when it comes to feedback devices for this application. You could have a magnetic encoder, a capacitive encoder, a resolver, or an optical encoder. And that's what we're going to be talking about today. So there are three main types of optical encoders. You can have a transmissive shadow encoder, a reflective shadow encoder, or an interferential optical encoder. Now, interferential optical encoders lead in resolution and in accuracy, but transmissive encoders are the most common types of encoders out there right now. So what are customers typically looking for out of an encoder? Well, usually they're looking for one that can provide high resolution and high accuracy with a low power consumption. But they're also probably looking for one that's a small form factor, one that's easy to align, easy to install, and one that is lower cost. So let's quickly take a look. We'll do a review of the transmissive optical incremental encoder. Now, this encoder utilizes LEDs as the light source, and it has this moving disc with transparent and non-transparent lines. So as this disc rotates, light is transmitted through that disc and onto two sensors. We have sensor A and sensor B, where sensor B is offset from sensor A by 90 degrees. So when we look at the light intensity on these two sensors, what we see is a sine and a cosine wave. But there's a problem with transmissive optical incremental encoders when we talk about achieving high resolution. And that's because you can only fit so many of these transparent, non-transparent lines on the disc before you start to experience this bleeding of light across adjacent transparent lines. Now, when this happens, it affects the purity of your sine and cosine waves. So to aid in that, masks are introduced, which are basically added behind the moving disc to prevent that bleeding across adjacent lines, maintaining the purity of your sine and cosine waves. But why so much talk about these sine and cosine waves? Why does it matter that we have these pure sine and cosines? Well, that's because these sine and cosine signals are used to interpolate and achieve high resolution in our encoders. So by interpolate, I mean basically taking the tangent of the angle, which is equal to sine over cosine. Now, theoretically, you could have an infinitely high resolution, but when we apply this, we are limited by the resolution of A to D converters, and we run into signal to noise issues. So to achieve some specific resolution, you'll need to interpolate to a certain degree, depending on the number of lines that you could fit on your scale. So let's take a look at an example. Let's look at a 50 millimeter scale and look at the case for a transmissive encoder. Now, the scale for a transmissive encoder will be able to fit about 1,000 lines, which is equal to 1,000 periods per revolution. Now, if we look at that same size scale, so 50 millimeters, but for an interferential encoder, we can fit about 8 times as many lines. So that's about 7,800 periods per revolution. So what that means is that in order to achieve the same resolution, we're going to need to interpolate 8 times deeper with our transmissive encoder. And when we interpolate that deeply, we run into signal to noise issues. So already we're starting off on a good foot with the interferential encoder. It allows us to achieve high resolution without having to interpolate as deeply as you would for a transmissive encoder to achieve that same resolution. So that's our resolution. Now let's talk about accuracy. Our accuracy of our encoders is dependent on the fidelity of your sine and cosine waves. So basically, how pure is your signal? Does it look like a sine wave or does it look like a square wave? We really want pure sine waves so that we can get the best accuracy out of our encoder. Now, additionally, accuracy depends on magnitude balance. If there's any phase shift, that would go on to affect your accuracy, and any offset. But these things are less of a concern than the fidelity because these can be calibrated out through gain offset phase compensation, which is built into our sensor circuitry. So that's not much of a concern, but the purity of the sine and cosine waves is a big concern. And you'll see that more as we start to talk about our interferential optical encoders. So before I jump into that, I want to do a quick review on some key light terminology. So I'm sure if we think back to old physics classes, we can pull this out of our brain and think of these 2 types of light. We have coherent light, which is light made up of the same wavelength, and light that has a constant phase, or a phase that is predictable. An example of this would be a red laser. And a red laser is also an example of monochromatic light, which means light of the same color, or more scientifically, light of the same wavelength. Now, jumping back to coherent light. As you see up here in the top left, we have all these sine waves drawn out to represent our coherent light. But that gets a little tricky when we start drawing these in more complicated situations. So instead of drawing these sine waves, we instead draw plane waves or wavefronts, which are these vertical lines here. And they are aligning the peaks of adjacent waves. And each wavefront is separated by a single wavelength. So it's just a convention that we use to simplify the drawing, and you'll see this used later on in the presentation. So that's our coherent light. But then we also have incoherent light. And incoherent light is made up of waves of varying wavelength, and its phases are unpredictable. At any given time, you don't know what the phase will be. And an example of this is an LED. So like we saw with the transmissive optical encoder, that utilized an LED. And for our incremental optical encoders, our interferential optical encoders, we are going to be looking at coherent light. So what happens when 2 waves interfere? Well, there is one perfect instance where you have the peaks of 2 adjacent waves perfectly aligned and the troughs of those 2 waves perfectly aligned. Now, in that case, the sum of those 2 waves has an amplitude that is greater than the amplitude of one of the incident waves. And we can see that here on the bottom right. Now, in all other cases where the peaks are not perfectly aligned and the troughs are not perfectly aligned, you get what is called destructive interference. And in this case, the sum of the incident waves has an amplitude that is less than the amplitude of a single incident wave. And we see that on the left there. And so if we visualize that, we can think about, like we see here on the left, if we drop 2 rocks into a pool, we'll see those waves, and as they approach each other, they start to interfere and cause these points of high amplitude and points of low amplitude. And that's really all that it is that's our wave interference. So now let's introduce a diffraction grating. And let's assume that this grating has slits that are very small relative to the wavelength of the incident light. And if you look here on our left, you see these monochromatic plane waves. So like I said before, these are all the vertical lines which symbolize the contours of equal phase of adjacent waves. As these monochromatic plane waves are incident on our grating, spherical waves are created from those point sources, and they begin to interfere, which we see here in this visualization. You could see these high points and low points. And when we talk about this with respect to light, we can think of these high points and low points as brightness and darkness. And that's what we'll see when we get into our interferential encoders. So one last thing to note here is that the same phenomena is experienced if instead of now having your incident light coming from the left, now let's look at incident light coming from the right. And instead of having these slits, now we'll have reflective surfaces. And again, the reflective surfaces are going to be very small relative to the wavelength of the incident light. These reflective surfaces are going to act as those slits did, and spherical waves are still going to be created, and we're still going to get these this interference pattern as the waves interfere. So what does this look like under a microscope? It'd be really cool if we could see light on that level and actually see the interference pattern. Well, this is where your mind will be blown, because this is the Talbot image. It is just a beautiful picture. I won't be surprised if you print this out and hang it on your wall, because it's just glorious. But there's this really special thing that happens when you have some certain distance away. The interference pattern is the exact replica of your scale. So what you see here on the left is this scale pattern. And if you look over on the far right, you have the same exact scale pattern. It's the same pitch and it's the same phase. So it's essentially an image of your scale. And we could put a moving detector on that Talbot plane and we'd be picking up the scale. So this same Talbot plane distance is repeated on factors of that distance. So you could have 2 times the Talbot distance, 3 times the Talbot distance, and so on. And if you align at that plane, you're always going to get the same image as the scale, which is mind-boggling. It's crazy and it's wonderful. So let's see how this is implemented in interferential optical encoders. So it is so basic, and that's what makes it really beautiful, is that all you have is your read head made up of a laser and a detector, and you have your scale, which is your diffraction grating made up of lines of reflective surface and non-reflective surface, and that's it. So what this means for you is that this is a really small package. You don't have any additional components, making it lower cost, lower weight, and that is just a beautiful thing. But we've got a bit of a problem, because if you think back to a few slides ago, I said resolution and accuracy are so important. And what affected those? It was our sine and our cosine waves. But you might have caught this in the previous slide, but we don't have a sine and cosine wave here. Instead, at our Talbot plane, we have what appears to be a square wave, right? We have these really bright blobs followed by darkness, and bright blob and darkness. And there's not really this sinusoidal gradient of light happening. It's more of a square wave. So let's dig a little deeper and let's try and understand why this is the case. So like I mentioned before, these point sources create spherical waves. And if you align contours of equal phase on these wavefronts, new wavefronts are created, and they can be thought of as beams of light coming out. So this diffraction here, this is your 0 order, and it's coming out perpendicular to the grating. Just a direct beam of light coming out. That's pretty easy to comprehend. But now we need to think about, are there higher orders? And the answer is yes. Of course, there are higher orders of diffraction. But because our scale has a 50% duty cycle, meaning the same width of the reflective surface as the non-reflective surface, our even numbers of diffraction are canceled out. We don't need to worry about those. But we do need to worry about the first, third, fifth, and so on. So let's take a look at this first order of diffraction here at the top. So what you see are contours of equal phase now delayed by 1 wavelength. And what essentially this is a beam of light coming off at an angle. But now let's take a look down here at the bottom. We have our third order of diffraction. Now these contours of equal phase are delayed by 3 wavelengths. So now you have this beam of light coming off at an even steeper angle. And so what happens when these higher orders of diffraction interfere with your 0 order, which is just the perpendicular beam to the grating? Let's take a look. So let's first look down here at our 0 order diffraction interfering with our first order of diffraction. You can see the first order is coming off at some angle. The red lines indicate the peak of the wave, and the dotted lines indicate the trough. So what you get when these two interfere is a sine wave with some certain frequency and some amplitude. And we can see that here on the left. That is our red plot. It is called our fundamental sine wave. It's what we want to be a perfect sine wave. But now let's look at the case of the 0 order and the third order harmonic interfering. Now, like I said before, because the third order is coming off at a steeper angle, you see that the sine wave that is created is the dots are closer together, meaning that it's a higher frequency sine wave and it has a lower amplitude. And you could see that on the left in green. And the same is true for the fifth order, even at a steeper angle. So the frequency is going to be higher and a smaller amplitude. But these higher orders all combine and they distort the fundamental sine wave. And what we're left with is an approximate square wave. And that's what we're seeing at the Talbot plane. Remember those bright blobs with immediate darkness and not really a gradient or a sinusoidal pattern. So what we need to do to get our high resolution and our high accuracy, we need to find a way to get rid of those higher order harmonics so that all we're left with is this pure, perfect sine wave. So let's first take a look at how we remove the fifth order and higher harmonics. So the way that we do that is through propagation filtering. So like I said before, we can align our sensor at any multiple of the Talbot plane. So we could align it the first, the third, the fourth, the fifth. It's up to us to decide where we want to align it. But if we choose to align it at the fifth plane, we're allowing these higher orders to propagate outwards and essentially miss the sensor. So by the time that they get to the sensor, they have really little impact on our fringe pattern. So it's a great way for us to get rid of those higher order harmonics. And now all that we're left with is the third order harmonic and our fundamental, which is what we need. We just need that fundamental. So what are we going to do? Well, through a patented design, we decided to make the sensor the same width as the third harmonic wavelength. So what you see here in gray are snippets of the sensor at different positions. So as the read head moves relative to the scale, these are the different positions. And what you'll notice down here on the bottom, we're taking a look at our third order harmonic. The sum of the light intensity on this sensor is always the same. It's never going to change. But if we look at our fundamental up at the top at different positions, it's always modulating. So essentially we're able to cancel out this third harmonic through this geometric filtering, which is a beautiful thing. It was a wonderful patent, and it's just a great solution. So now what we're left with is this sine wave. But like I said at the beginning, it's all about the sine and cosine. So how do we get that? Well, we get that through signal processing using 4-bin sampling. So now we take 4 different detectors and we overlay them across 3 fringes. Now each sensor still, like I said before, is the same width as the third order harmonic wavelength. So we've already gotten rid of that. We don't need to worry about it. But now we do 4-bin sampling, which basically we're taking A minus B and A minus C and B minus D. And through that calculation, we end up with a sine and a cosine wave that is centered about 0. And additionally, to improve subdivisional error, we do quad pack averaging, which is essentially taking more samples to improve the signal. But there's still one thing to mention here. And up until this point, I've assumed that our scale is glass. But what if we have a tape scale? Well, we know that tape scales are more rigid. They have more imperfections than a glass scale, so they look a little bumpy. What this does is it causes fringe to fringe variation. So what you see up above is very exaggerated. It won't ever look this bad, but this is just to show you what happens with tape scale. There's slight imperfections. It causes phase and amplitude variation. So when we go back to this 4-bin sampling, we see here we're sampling across 3 different fringes. So if there's any variation between those 3 fringes, it's going to affect our sine and cosine waves. So to further improve our signal, we need to find a way to only sample a single fringe. And the way that we do that is again using a patented design, which is the zigzag sensor. Now, this utilizes this zigzag pattern to cover a single fringe across these 4 sensors, while still covering the third harmonic wavelength across a single sensor. So again, we're able to do our 4-bin sampling. We take A minus C, B minus D, and do some quad pack averaging. And we're left with sine and cosine centered about 0 with an improved signal, because we don't have the fringe to fringe variation affecting that. So it's a wonderful thing, and it is implemented in our Talbot imaging interferential encoders. So that's it. That is our Talbot imaging interferential encoder. If we were to compare this to a typical interferential encoder, you'll see that there's less components. We don't have collimating optics and filtering optics that are needed. Because it's a laser, it's going to be running cooler, have a lower power consumption, and retain light intensity for longer. It's just a simpler construction, meaning it's going to be lower cost, and it is easier to align, meaning it has wider Z height tolerances. And that is it. So with that, I am going to check in and see if you guys have any questions. And if there's any time left over, I will get to them. But if not, then I will email you guys some responses if I run out of time here. Okay, so the first question is, are there disadvantages to Talbot image encoders? Yes, there is. So Talbot image encoders rely on this diffraction grating, which is made up of reflective and non-reflective surfaces, like I mentioned. So if you have any kind of debris on this scale, it's going to affect your signal. So If you're operating in an environment where there's a lot of debris, like in milling or CNC, you might run into issues if there's grease involved. But if you're working in a clean, contained environment, like a robot joint, for example, then this is a great solution. So there is a disadvantage in that you need to maintain a clean scale. Okay, another question. What determines the Talbot distance? So let me hop back to that slide. So the Talbot distance is directly related to the pitch and the wavelength of the incident light. And the exact equation is equal to 2 divided by wavelength times pitch squared. So the smaller your pitch is, the closer you're going to have to get to the scale. So that would be the only downside of scaling down the pitch of your scale. Okay, those are all the questions that I've gotten. So with that, I will wrap up this presentation. Again, I want to thank you guys so much for joining. It was a lot of fun for me to talk about this, and I hope that you find this as interesting as I do. Maybe you'll tell some friends about it and post this Talbot image picture on your wall so you can remember it forever. Hope you guys have a great day. Thanks again.